Hey guys, welcome back to another video. So in this video we're going to be doing intermolecular forces. I'm sort of sorry about the break I've had. I've been kind of dying through college apps, so let's do this. Um, so for intermolecular forces, I'm going to start by telling what they are, and then I'm going to talk about the three main types of intermolecular forces and then relate them to the properties in molecules that we already know. So let's start with what intermolecular forces are. So IMFs are nothing but the forces between molecules. So intermolecular forces, so let's say you have like a molecule like chlorine, okay? Let's say, okay, and we have a bunch of these chlorine molecules. Okay, so these solid lines are bonds or intramolecular forces, and these dashed lines are between molecules, and these are intermolecular forces. So the one thing I want you to get out of this is that intramolecular forces or bonds are a lot stronger than intermolecular forces. So a good comparison I like to sort of say is IMFs are weaker than covalent bonds, which are weaker than ionic bonds. Yeah, so there are sort of different types of intermolecular forces, and let's start with the first one. So the first intermolecular force that we have here, like I said before, is London dispersion forces. Now, London dispersion forces are by far the weakest IMFs, just because they're called temporary dipoles. So let's look at the nature of London dispersion forces. So this is helium, okay? Helium has 2 electrons, right? So normally, let's say random helium electron. But electrons like to move a lot. So what if there are more helium electrons on this side than on this side? So this actually forms a dipole where this is negative and this part's positive. Now, what if other instantaneous dipoles happen? Then you get a weak sort of attraction between molecules of helium, for instance. And the reason these are so weak is because it's just one electron sort of making this attraction, but it's still an attraction. And many of the times, electrons move back into place anyway, so that's why. So the one thing we need to keep in mind about London dispersion forces is that as the molar mass of any sort of molecule increases, as molar mass increases, so does the London dispersion forces. Just because there are more atoms, they're more likely to form dipoles like this. Now, another thing you really need to keep in mind is that London dispersion forces are in everything. Nonpolar, polar, it's in everything because instantaneous dipoles can happen to any molecule. So the next strongest intermolecular force is called dipole force. The thing about dipole forces is that they're only in molecules with the permanent dipole or polar molecules. So nonpolar molecules do not have dipole forces. An example of this would be something like water. right? H2O. It has a permanent dipole just because there's more electron density here, so it's negative, and this stuff is positive. Molecules are attracted by this, right? Because this is positive, negative, positive, negative, and then so it's just anything with a sort of polar permanent dipole, because they're sort of different densities of electrons, they get attracted. And that's basically the premise of dipole-dipole forces. Dipole-dipole forces, like I said before, are stronger than London dispersion forces. The way I look at hydrogen bonding, the last main component of intermolecular forces, is it's sort of a stronger form of dipole-dipole interactions, the way I look at it. So any hydrogen interaction with nitrogen, oxygen, or fluorine is a form of hydrogen bonding, where there's such a large difference in electronegativity between these that there's a stronger attraction and a greater intermolecular force. So let's revisit water for a second. Right, so water, it definitely has dipole-dipole interactions. But as you see here, it also has hydrogen bonding, because this is an oxygen, this is a hydrogen, and there's hydrogen bonding. So the way I think about intermolecular forces is that in water has both London dispersion forces, dipole-dipole interactions, and hydrogen bonding. It has all three, but the most pivotal sort of type of IMF is hydrogen bonding in water. So any sort of molecule with hydrogen bonding, you'll notice that is very hard to break apart the molecules. And that's some sort of a precursor we'll look at pretty soon on how a stronger intermolecular force between molecules affects the properties we know. So some of the properties that are influenced by IMFs are boiling point and vapor pressure. So boiling point, the sort of proper definition, is the vapor pressure of a liquid when it equals the external pressure. That's sort of really confusing, but basically what we know boiling point is the temperature at which a liquid boils and turns into vapor. So liquid to vapor. That's what we're looking at. Now the relationship with intermolecular forces is actually pretty logical. When you have liquids that are really strongly cohesive, so like let's say they have high intermolecular force, it's going to be harder for the molecules of liquid to break free and become gas molecules, right? So the relationship is essentially the greater the IMS, if IMS are strong, then they will have a greater boiling point, because it'll take a higher temperature for the molecules to break free just because they're so cohesive. So boiling point will increase. And vice versa is also true. Now the second thing is that we're going to look at is vapor pressure. Vapor pressure is actually kind of difficult to understand, but it's basically the pressure of a vapor when it's in contact with its liquid form. So this is something sort of different. as the intermolecular forces of a substance is greater, then it's going to exert a smaller force to its liquid. So let's look at this problem. So they're asking to arrange these 5 molecules from least to greatest boiling point. So we know from our previous relationship, the greater the intermolecular force, the greater the boiling point. So let's put these 5 molecules from least to greatest intermolecular forces. So the way I like to start these problems is to first sort them by polarity, so nonpolar and polar. And usually nonpolar have lower intermolecular forces and usually have a lower boiling point. So let's start by looking at polarity. So C60, Buckminster fullerene, is a allotrope of carbon. So allotrope means sort of like a different form of a carbon. So carbon has a bunch of allotropes like diamond and graphite. So C60, that is nonpolar. So that's nonpolar. Here, let's put this back to. That's nonpolar. Sodium chloride isn't polar on nonpolar. It's ionic, so it's extremely polar. Argon is nonpolar, helium is nonpolar, and dinitrogen monoxide is polar. So let's get back to C60. NaCl is an ionic compound. They don't really have intermolecular forces as much because they're so strongly bonded because of the electronegativity difference. So this is sort of like a bond. So we'd expect sodium chloride to be at the top or the greatest, because the rest are just covalent molecules and they experience intermolecular forces. This is an actual ionic compound, so this will definitely have the greatest boiling point. Argon and helium, both are nonpolar, so both of them only experience London dispersion forces, and so they have probably the lowest intermolecular forces. Now, to separate these two, we have to look at molar mass. Helium has a much lower molar mass than argon, so helium has the lowest intermolecular force. Next, we can probably put argon. Dinitrogen monoxide, it's polar, so it experiences dipole-dipole forces plus London dispersion forces. So dinitrogen monoxide and carbon C60 is left. Now C60 is nonpolar for sure, and so we'd expect C60 to be before dinitrogen monoxide, because that's what I said, right? But the thing with this problem, that really tricky part, is C60 has a molar mass of 720 grams. That's a huge amount of intermolecular forces right there, just because it has such a huge molar mass compared to the rest. So actually, we'd expect dinitrogen monoxide to be before C60. Normally, if this was something like, I don't know, like chlorine, a chlorine diatomic atom, or something like that, then it would definitely be before dinitrogen monoxide. But just because this has such a huge molar mass, then it's gonna be a little higher than dinitrogen monoxide. So the second question, I'm pretty sure we've already answered, is which IMF is prominent in each. So for C60, just because it's just carbon molecules, it's nonpolar, so it's just London dispersion forces. Sodium chloride it's none of them. It's an ionic bond. So dinitrogen monoxide, dipole dipole. So when they're asking which is most prominent, it's the stronger IMF that it has. So dinitrogen monoxide has both London dispersion forces and dipole forces, but because dipole forces are stronger, it's more prominent. Argon, it's nonpolar, so it's London dispersion forces, and the same thing with helium. Okay, that's it for the video. Hope you guys enjoyed. See you in the next one.